Well, hello and welcome back to Engineering 202. I want to talk about experiment number 1 and go through that and get the data to you so that you can go ahead and make the most of it. I'll be sending the procedure to you, and this is again very much similar to how we handled the laboratory last term in Engineering 201, but I'll be sending the procedure to you and the question sheet and also the data and the supporting material. But on experiment number 1, what we've done here is basically our circuit is this part right over here, like this, really just one loop, and then we're measuring it with the 2-channel oscilloscope. And I'll mention in both experiment 1 and experiment 2, I'm not going to go into too much how we make the measurements with the oscilloscope. We talked about that some in laboratory number 6 last term, and I'll probably devote some time to that in laboratory number 3 this term. That laboratory is probably a little bit easier in that regard, and we can put a little more time into that. But in labs 1 and labs 2, I really want to concentrate on where, or excuse me, what we do after we get the data. So that's how we'll break this up and go forward from there. So anyway, this is what we're going to do, and inside this box here we will put a variety of different elements. We could have element number A, which is going to be a resistor, or element number B, which is an inductor, and really remember that an inductor is an inductor, and then it always in a real sense has some resistance. Then we'll put a capacitor, and we'll find that the capacitor doesn't suffer from this internal resistance as much as the inductor does. And then to mix it up a little bit, we will add a capacitor and a resistor. And one of the things that will help us to go through this is by having this sampling resistor down here, we'll be able to figure out what the current is quite easily. So one of the things that I did when I set up this experiment is I measured carefully this resistor, and while I wanted 100 ohms, I only got 99.5, so that's not too bad. So in my calculations, you'll see me dividing by 99.5. That's where that came from. And then this resistor here, R2, or this resistor that we tack on to the capacitor, that's R2 or R3. I wanted 220 ohms, but I only got 216, and that's okay too. The inductor that we're going to do, element number B, is 500 millihenries, so that's a half of a henry. And the big thing there is that it has some pretty significant resistance. Maybe we'll put 1/2 henry there. Let me look up that resistance. I measured that. I've got that over here on this other document. That was 561 ohms. So 561 ohms, okay? So, and you'll want to jot these down from the video. I'm probably not going to provide those in any other place. It seems like that some people probably last term just kind of looked at the data sheet and winged their way through the lab. I think there's some value in actually going through the video, so I'm going to provide the data via the video in that regard. I've got some pictures that I will certainly share with you, but in terms of the internal resistance of the inductor and these values here, you'll want to get them from right here. So that's what we're going to do with that. And before we go on and finish that up, let me talk a little bit about something I talked about. This was in lecture number 4. So if you go and look at lecture number 4, and I'm just looking at the PDF, but I would definitely refer you to the video. I spend the first few minutes straightening out a mistake I'd made on lecture number 3 about the phase shift, and that's probably as applicable to this as anything. So that's certainly not a waste of your time starting through that. And then I very quickly go into how we're going to work on this lab, and you can see where I have put the unknown impedance here, and then I've got the channel 1. Remember, this is going to be channel 1, and then I've got channel 2 there, And by using channel 1 and channel 2, if I subtract channel 2 from channel 1, I get the voltage that is across this. Okay, that's that voltage there, V. And if I take channel 2 and divide by the 100 ohms, now it's not exactly 100 ohms, in our case it's 99.5, I will be able to get the current. Well, of course, if I find the ratio of the voltage to the current, that gives me the impedance. So I can figure out what the unknown impedance is by this right here. And I will reproduce this in more detail as we go through this lab and actually go into it with numbers. But if you're wanting a little different twist on this, I go through this in lecture number 4. So I wanted to bring that to your attention. So what we're going to do then in this laboratory is I'll connect the circuit as shown. That was this circuit right here. And I was going to use a sine function. I believe we were running this thing at 60 hertz, so that's the same as what's coming out of the wall outlet here. If you go other parts of the world, it might be 50 hertz, but 60 hertz is pretty common. So we're going to build that thing. They're going to use a sine wave, find a voltage which gives good results and does not exceed current ratings. So I'm going to use somewhere less than about plus and minus 5 volts, probably quite a bit less than that. But if I look at this sine wave here, if this is minus 5 volts and this is plus 5 volts, that would be a difference, what we would call voltage peak to peak, of 10 volts, and I'm going to be quite a bit less than that. Okay, so that would be my absolute maximum, and I checked a couple of the components and whatnot. I think we're in pretty good shape with that, and using a little different equipment than we normally would use in lab and whatnot. So I've changed some of the values a little bit. So anyway, so we'll set that up, and then we'll swap out that unknown inductance to B and C and D. And that's, you know, it's a little bit contrived. When we put in this R2, we really know what it is, but that's a mixed blessing because now that we kind of know what it is, we're going to have to test it and make sure that we can figure out and come to a right conclusion. We say that it is what we know it is. And then, like I said, we'll switch to B and C and D. So I'll refer to those as A, B, C, and D. Okay. Pretty straightforward with this. In fact, we're going to be doing a similar lab to this in laboratory number 2, except with that one I won't be changing the elements so much, but I'll be changing the frequency, and we'll see how this changes with frequency. So that should be a good experiment too. Some of the requirements we're going to have to go through, and some of the nomenclature. We're going to want to determine the values of resistance, and then there's always the this X sub L. That's kind of a shorthand for omega L. Of course, L is the inductance. X sub C, that's the shorthand for minus 1 over omega C. And I guess if you're thinking, well, the shorthand XL for omega L doesn't make it much shorter. This one, probably there's some value there that X sub C is minus 1 over omega C. And finally, the exact value for C. So if you're stumped on X sub L and X sub C, that's what's going on there. And we'll do the phasor diagrams and impedance triangles for the elements. So this is our question sheet here. I think I'll set that aside and wait till we've gone on through our laboratory, and I'll wrap up the lab with this and what's expected of you on that. So this is the data, and like I said, there's some data here that I'm just figuring you're going to get from this. The internal resistance of that inductor, 561 ohms. R1 is really 99.5. R2 and R3 is 216. So make sure that you pause the video, copy that down, however you do that. But I will be sharing these, and they will come to you in color, but I tried to annotate them such that if you're not very good at distinguishing colors, which is, is a big deal. A lot of people aren't very good at distinguishing colors, and certain colors they have a hard time, and they might not consider themselves colorblind, but they might have a hard time distinguishing between a couple colors that are somewhat similar. So I've tried to make this so, one, you could print it out very economically with black and white, but two, so that you're not reliant on colors. So this is element A. This is the resistor. So I'll just put some notes on this thing. This is the resistor. So we would expect, and when we have channel 1, that's the larger one, and if you're looking at this in color, that's the yellow one. So this is channel 1. And then this guy over here, the smaller one, that's channel 2. And one thing, this is one of the, it's always kind of humorous to watch students in lab, and I miss seeing you, and I miss interacting with students in lab. But one of the things that was always fun to do was to have students set this up, and a student would always come to me rather panicked that yeah, there's no phase shift, that these are in phase. And I go, well, what element are you working on? Oh, well, we've got element A, a resistor. Well, what are we expecting the phase shift on a resistor to be? 0. So we know that theta is equal to 0 degrees, that there is no phase shift here, that these cross at the same point, they're rising and falling at the same time. So theta is equal to 0. So that's an important thing to take away from this. Now I'm not going to go through all of the other calculations on this. I'm going to pick a little more complicated element to do that. In fact, I'm going to do element C. But you can go through this, and hopefully you will be able to then say that our impedance in there, when we put this 220 ohm resistor in there, we will come out with the resistance is equal to something, and hopefully it's pretty close to 220. I think that will be a good exercise. Now this one here, this is element B, so that was the inductor. And remember that any inductor has a lot of resistance. Okay, so that was element B. And again, we have the channel 1 and we have the channel 2. And maybe I'll pop back here to this one. This was kind of another good one to start with, is the scale for channel 1 was 500 millivolts, or half a volt per division. And when we say a division, that's this centimeter distance there, whether it's a vertical division for voltage or a horizontal division for time. So 500 millivolts per division. So that far is 0.2 milliseconds. Okay. And this far is 500 millivolts. Okay, half a volt. And likewise, channel 2 has the same scale. So this is the channel 1, and this is the channel 2. So those are both on the same scale. Now, when we go to this one, the scale has changed. Channel 1 is now 1 volt per division, and channel 2 is 0.2, or 200 millivolts per division. So you have to be careful with that. So the larger one, and when I say larger and smaller, I'm not factoring in this factor here. I'm using this just as a way to distinguish these graphs here without having the advantage of color. When you see these in color, you'll see that this channel 1, this is yellow, and this will be a yellow line, and this one is blue. And then this will be a blue, I shouldn't say line, but curve or sine wave. So that's what we've got there. So we need to start being very careful with this. While they may look like they're about the same, they certainly are not, because their scale factor is different. We have to be careful of that. Now we're running at the same frequency, so we would expect this distance here, our time base, to be the same. And indeed it is, 0.2 milliseconds per division. So that's element number B. Element number, or letter C, that's the capacitor. So we've got the capacitor there. I believe that was 2.2 microfarads. Remember that micro is 10 to the minus 6. So that's what we got going there. And as you would expect, again, keep kind of seesawing back and forth here. Element number, or element A, that was the resistor, no phase shift. element B, that was the inductor. We see that channel 2 is ahead of channel 1. And finally then here with the capacitor, we see that channel 2 is behind channel 1. So we not only have phase shifts, we can think about that leading and lagging relationship, and it should not surprise us that this is an inductor and this is a capacitor. Well, as I mentioned before, I want to go into more detail on this one. So I don't want to do all 4 of them because that would not then leave any lab for you to do. But I want to do this one, and we'll see why I picked this one. It's not certainly not the easiest one, and has a few peculiarities that I think it'll be good that we are together and talk about. So one of the things that I want to do is I want to figure out the amplitude of that right there. Okay, so the distance right there. And then I also want to do it again right there. Because remember, when I was going through this, I wanted to figure out what channel 1 was, and I wanted to figure out what channel 2 is or was. And I may refer you back to this diagram here. It's very similar. So there's our resistor, 99.5, and by taking the voltage of channel 2, I'm going to take it as a reference of 0. So I mean, you could say it was some odd angle and then this has shifted yet further, but why make life miserable? Why don't we take one of these as 0? We could take this as 0, or we could take this as 0. This I'm actually going to have to do more calculation with, so I think I'll take this as 0 and then take this angle as whatever our phase shift is. So I need to find this voltage here, V2, if you will, which is going to have some amplitude at some angle, which will be theta. Okay, so if I come back here, if I find this, that's the amplitude, and I'm going to reference that. I'm going to say that that is 0. And then this one here, I can have V1 is going to be some amplitude, and it's going to be whatever. I'll make this 0, and I'll leave this at theta. So I've taken V2 as a 0 angle, so whatever that theta, I've taken that as 0. This one I'll have to calculate, and I need to get the amplitude there for V1. So that's right there, isn't it? Okay, so let's see if I can go through that then. Slip over here and grab something. So I'm going to use the scale on the graph, the oscilloscope plot, to get through that. Let's see. So I could talk about my notes over here. So I could say that for channel 1, I have what? I know that I have a 1 volt for division. And how many divisions do I have there? Well, from here, it's symmetrical on here. So I mean, I could go from here clear up to here, and that would be peak to peak. But I really just want to do this, that being the amplitude. So I'm going to have 1 division, 2 division, 3 division, and then if I start looking at these individual little tick marks, there's what, 2, 4, 6, 8, 10. So I get 0.2 for each one. So 1, 2, 3. It looks like about 3.7, right? And if you came up with 3.6 or 3.8, that's fine. This one is a little harder because there's some noise and whatnot. We'll get through that. So that's 3.7 divisions times 1 volt per division. That's where the 1 came from. Gives me 3.7 at an angle of minus theta. Okay, and I know that this is negative because it's a capacitor. If I go back to the inductor is going to be positive. This will be positive theta. Okay, this being the inductor one. With the capacitor, it's negative, because I've got that switching. And laboratory number 3, that's going to be a fun lab. We're actually going to see them switch on screen as we talk about power factor and going from a inductive to capacitive and vice versa. But so that theta is negative. So I have 3.7 at minus theta. Of course, that's volts. That's channel 1. Now, if I look at channel 2, let's see what we have there. I've got how many divisions? It looks like about, what? And this is kind of hard. I usually just kind of eyeball a line down the middle of this because there's just some high frequency noise in there. But it looks like I got 1, 1.5, probably about 1.6 if you really look at it close. And I've got the pictures that I've sent you are better than this black and white plot that I have here. But 1.6 times, what do we have? 200 milli. So this is 0.2. 200 milli is 0.2 volts. So this turns out to be equal to, what do we have? 0.32. Yeah, okay. 0.32 at an angle of, we said this was going to be 0. That's our reference. Okay, I mean, we could take some odd angle, put this at 13, and then this would have yet a further shift, but we'll make that 0. We'll make this theta. Well, speaking of that theta, let's go about and find that theta. So I've got this answer here. I've got this answer. I need to find theta. Well, let's see if we can work through that. So one thing that I want to do is I want to figure out the frequency here, because it may not necessarily be 60 cycles. I mean, I wanted 60 cycles, okay, but I may not have got it, because I mean, I may have been just a little bit off on the adjustment. So let's look at this. We could pick either one of the waves. I could pick this wave, or I could pick this wave. This one is a little tidier and a little nicer line, so I think I'll use it. So I'm going to say it goes from here. There's 1 division, 2 division, 3 division, 4 division, and it looks like about 4.5, 4.5. Okay, so I'm going to say that 4.5 times, what do we have here? We had 2 milliseconds per division, so 2 times 10 to the minus 3. So what's that turn out to be? 9 milliseconds. Okay, 9 milliseconds. So that's the time it takes to go from there to there. That's 180 degrees. That's 9 milliseconds. So I think we're okay with that. We could, you know, and if you come up with 4.4 or 4.6, you're probably going to be okay. So what I want to do with that is I know that the frequency f is 1 over the period t, which would be 1 divided by 2 times 9 times 10 to the minus 3, right? I mean, this is 9 times 10 to the minus 3 seconds. So if I'm using base units, that's where that is. Where in the world did 2 come from? Well, this is only half of it, right? And this is a half, or 180 degrees. I could, if I wanted to, measure from there to there. I just have to count further, and that'd be fine. But that's where the 2 comes from. So when I go through that, that turns out to be 55.6 hertz. And then I'm going to multiply this. We want to get radians per second. Well, I guess it's probably worth a little bit commenting about this. 55.6, it's certainly not 60, but we're fairly close. As long as we know what it is, I think that's okay. I'm going to go ahead and then multiply by 2 pi, and that gives me then 349 radians per second. So that's our omega, right? It's not 377 because it's not 60, but it's fairly close. And the important part is that we know what it is. I'm going to grab my calculator here and just double check a couple of these numbers, make sure that we are good with them. I think we're okay with that. So the last thing then that I need to do is figure out that theta. So I could say then by ratio and proportion, right, that theta is to some distance here, right? We're going to have some phase shift, and I could find this distance, or I could find that distance, or I could find this distance, because this wave's going down and that's going down. This is going up, that's going up, this is going down, that's going down. I wouldn't want to take this one in here, and that's what I talked about when I was talking about this lecture here, that I had inadvertently put that was theta. That's not true, because one wave's going down and one's going up. So likewise, this would not be theta because one's going down and one's going up. So I have a lot of places to measure that theta. I think I'll do this one. That's probably just as easy. So let me do that. I could say then, looking at that, what do I have? I've got one division. I've got two divisions. Looks like just a little pass. Why don't I call that 2.2? And remember, it's 2 milliseconds per division. So I'm going to come down here and I'm going to say that I have 2.2. That's from the number of divisions. As I said, this is 2.2 divisions across there, times the 2 times 10 to the minus 3 seconds. That's 2 milliseconds per division. That was our scale right here. So when I multiply that out, that gives me what? 4.4 milliseconds. And I'm going to keep that in milliseconds because I've got this in milliseconds, and I think that should work out okay. So I'm going to say that my phase shift in terms of time is 4.4 milliseconds, whereas 180 degrees is 9 milliseconds. By ratio and proportion, I should be able to get this. So I can say that theta is to 4.4 milliseconds, as 180 degrees is to 9 milliseconds. And I don't have to go back to base units because the units will cancel as long as they're the same. So if I use seconds for both of them, that's fine. If I use milliseconds for both of them, that's fine. So I go through that and I find out that theta is equal to 88 degrees, 88. Okay, so let me double check that. Yeah, good. So I really didn't need the calculator on that, but so that's 88 degrees. So I think we have all the pieces here because I can now say that this is 3.7 at minus 88. Okay, so that's my voltage 1. Here's my voltage 2. That was at 0. And I've got my phase shift. So coming off my graph then, I've got that information, and I should be able to then work through this. Okay, so I've got that this is 3.7 at minus 88, that's volts, and this was 0.32 at 0 volts. And I can start working my way through here. And again, if you go back to this lecture number 4, I'm going to work my way right down through here. Okay, if you don't want to go back to lecture 4, that's okay. I'll probably give you enough steps here that you don't need to. So this current I could say that I is going to be equal to, it's going to be equal to the voltage 2 divided by that 99.5. I mean, this is Ohm's law. This I is equal to V over R, right? Or V over Z. That should be a little more general. V over Z, where our Z is just that right there. This is the Z for the resistor. R equals 99.5. It's not the impedance up there. In fact, I'm going to go back and maybe I subconsciously knew that I really wanted R. I wanted that 99.5. Okay, so let's do that. We'll put this 0.32 at 0 in here and divide by 99.5. That's volts, that's ohms. So when we go through this, we should come up with 3.22 at 0, and that will be milliamps. So I multiplied by 1,000 there because this is going to get to be a pretty small number to get the milliamps. Okay, so now I can talk about this voltage V there. I could say that voltage, V, is equal to the total voltage, V1, minus this voltage, V2. I mean, that's just Kirchhoff's current law. From there to there, if I subtract then from there to there, I get the remaining portion. So I say that this is 3.7 at minus 88, and then I have to subtract off this 0.32 at 0 right there. And that gives me then 3.7 at minus 92.9, and that's volts. Okay. So let me double check that. Yeah, I think we're okay with that. Okay, so we've got that, and we might take a moment to start to, well, let me finish up here. So now the impedance Z, and this is again from Ohm's law, Z is equal to voltage divided by the current, right? So I'm going to take this 3.7 at minus 92.9, and I'm going to divide by what? The current. 3.22 at 0. So when I do that, and I'm going to actually then convert into a rectangular form, I get minus 59.3 minus 1150, and that'll be ohms. Okay, let me double check that. This would be, let's see, I should probably be a little more careful here. This was milliamps, so I'd have to divide this by, what, 1,000? Because of the milliamps there. Then I think we're in good shape. Minus 59.2 minus 1148.36. Yeah, we're close enough to 1150. We'll just leave it at that 1150. That's a nice round off. So, okay, there's a few things, and then you'll start to see why I picked this problem. We've got a few little problems here. Remember, this is a capacitor, right? I mean, we knew that there was a capacitor in here. I've got this. I've got the capacitor in there. So we would expect the resistance of that to be, we'd like it to be 0, but it's not 0. And in fact, it's negative. And we don't want to try and go running off announcing that we've got some new physical phenomena of negative resistance. This whole thing probably comes from error. I mean, there's certainly places to get error in here. I don't. Hopefully, we don't have any gross errors in our calculation. We've tried to be careful of that. But with our measurements here, I mean, whether you had a 1.6 or a 1.5 or a 1.7, whether you had this 2.2 down here, this one's probably the biggest place where you can get error in this thing. So there's little places where you can get errors reading off of these graphs. But I think if we look at this, if we come back to this, I think we'll be a little more impressed with our answer than we maybe are initially. So while that comes from some errors in the measurements and whatnot, we would have liked to have got 0 there. But anytime that you're shooting for 0, if we would have got 3, we would have been really happy, right? Okay. If we got -3, then we would have been concerned because that negative sign seems to trouble us. But really, that's just because of the error. Let's look at what this is. Remember, this is supposed to be minus j over omega c. Okay. I should have probably been a little more careful here and put I'd have minus j in there, right? You have the real portion and the complex portion because I switched from polar forms to rectangular forms. So minus j over omega c. So this is negative, that's good. So I can say then that 1 over omega c is equal to 1150, or I think it was 1148, 1149, but we'll just call it 1150. And I know that omega, let's not say 377, let's go back over here. That's why we calculated this at 349. And incidentally, you'll want to do that calculation on all of the elements because it'll change a little bit. The source I was using was really not that great, and as I loaded it with different elements and whatnot, the frequency changed just a little bit. So with 349, I can calculate C from this thing. C turns out to be 2.49 times 10 to the minus 6, which would be 2.5 microfarads. Let me double check that for you. Yeah. Something like that. Well, how did we do? What were we expecting? We were expecting a capacitor here, the capacitor of 2.2 microfarads. Okay, so versus, down off the page here, sorry about that. So 2.5 versus 2.2 microfarads. So we could find the percent difference there. We're actually not too bad on that. I think our capacitor, I didn't have necessarily a way to test it. I was just going to take it off the face value. As far as the inductor, I did the same thing on there too. But I do know our capacitor is plus or minus 20 degrees. And if we look at that, we're well within the plus or minus 20 degrees. So I think we can be pretty happy with that. Okay, so that's good. Now, one of the things that we're going to be tasked with doing then is to come up with a impedance triangle in a phasor diagram. So for the capacitor, our impedance triangle is going to look something like this. That will be the impedance. This will be the R value, and this is our minus 1 over omega c. So this is equal to minus 1150. That would be ohms. Okay, and this one we'll say is minus 59.3 ohms, and we should probably put a note here that negative due to errors. Probably most of the errors in the interpretation of the graphs. Okay, and then that would be our theta, which turns out to be, what do we get for the angle of our impedance? Oh, I don't think I have that because I need to redo this. There we go. So this turns out to be 11, well, this is so small, it's really about 1150 at minus 92.9 degrees. So if we were to write this in a polar form, we'd get something like that, okay? So that's the angle in there. Theta is about minus 92.9 degrees. And again, if that fell right at 90, we'd be patting ourselves on the back how great we did. And if it was at 88 or 89, we'd think we were pretty close. It's just that our error tended to make us go over, in which case we ended up with a negative angle there. Okay, so we might extend that note to that also. Okay, now if I look, the good news is though is we're pretty close to 90, right? Okay. Incidentally, when you look at the inductor, it's going to have a lot of internal resistance. I mean, this, whether you observe the negative sign or not, that's not a very big value in comparison to that. When you look at the inductor, these two values are going to be approximately or roughly the same size. Oh, probably not quite, but they're going to be in the ballpark. So that's going to cause you to have a triangle that looks a lot more like a 45, not exactly 45, but more in that kind of a shape, rather than something that's very, very steep. I mean, I've exaggerated. I should have, if I was going to draw this more to scale, the triangle would look something like that, wouldn't it? Okay. Now, so that's the impedance triangle. Now I want to look at the phasor diagram. The phasor diagram is easy. I'm just going to put that on the real and the imaginary. So over here I put the real. And then up there I put the imaginary, and I always spell it wrong with a J. So we know that's the J-axis. And what do we have here? We're going to put the current. What was our current value? Right here. 3.22 at 0 milliamps. So there we go, right here. So we just put that right there. So that's I. And we might even say that that was 3.22 at 0 milliamps. And then what was V? Well, V is right over there, isn't it? 3.7 at minus 92. So that's going to put me right there. There's V, and 3.7 at minus 92.9 degrees, and that's volts. Okay, and just like these numbers up here, we have a little note on these. I mean, that should be less than 90, shouldn't it? Okay, so the good news is it's really close to 90. The bad news is we've gone a little bit past. But if I look at this then, what do I have here? I've got the current. The current is leading the voltage, right? So what do we have? Ice. We know this is a capacitor. So the pieces are all fitting together then. Okay? Well, I think, and the reason that I did this one is it's probably the most difficult one because you end up with this trouble here. If we go on and look at the next one, if you look at element number D is the same capacitor, and then we've added 220 ohms or 216 ohms to that. And so you should see on that one that the capacitance, this portion here, should remain about the same, but hopefully this will increase. Hopefully it will get up into some positive numbers. Okay, so I think that's going to be a good exercise with this one. And we don't want to get too hung up on some of these errors and things like that. We want to look at some of the bigger trends as we add resistance to that. Is that reflected in that number? And I think that you will see that it is. So that should be good. Let's look then. I think that's the last of the elements. So what are you asked to do then? If we look at the question sheet, so you get a question sheet like this. I'll send it to you in Word so that you can expand it. You may need more space in here. Use it. If it goes to 2 pages, that's fine. If you the calculations, I mean, granted, I probably could have made this a little more concise, maybe wrote a little bit smaller, but I'm probably going to need more space to put that into there. Okay. Actually, I did this one, didn't I? You're going to have to do this one, so you'll probably need a little more space, and you're going to want to check me out. You're going to want to make sure that I did that right. Okay, so let's see here. Make sure you put your name on there. Draw the impedance triangles for elements B, C, and D. We didn't put A because A is a resistor. That impedance triangle is really boring. Looks like an arrow, doesn't it? Okay, but B, C, and D should be a little more interesting. Inductors, they're going to look like that because this is positive. Capacitors are going to look like this because this is negative. Okay, so you can do that. I should have, there's our impedance triangle right there. Then we're going to calculate that, and you have to calculate these before you can draw the impedance triangle, so you're probably going to do this and then that. These maybe not in the right order. And then the phasor diagram for A, B, and C. I just left off D. I don't know why. I guess I had 3 up there. I'm going to have 3 down here. So what's the phasor diagram look like? Well, there's our phasor diagram. That's the phasor diagram for C, isn't it? So you're going to have to do the one for A and the one for B, and then also check up on me, make sure I did mine on C correctly. Okay, so take some time, write these out really nice. If you want to do them electronically, that's all the better. If you going to write them out by hand, that's fine. Don't just scribble them onto a piece of scratch paper and snap a picture of that and attach it to that. That's not what I'm looking for. I'm giving this to you in Word, so if you're going to do it by hand, scan it and or take a good picture of it and crop it in and put it in here and make it look impressive. Okay. Because this is your only deliverable right here. If we looked at doing the lab face to face, you'd be into this for 3 hours, right? So I think if you'd sit down and you take 3 hours to do this, you'd have a really very nice question sheet. The final thing, of course, is to sign it and date it. That's your signature. I know what my signature looks like. I want your signature on there, and then scan the whole thing and turn it in. Should be good to go. So, like I said, I did element C for you right there, but you'll want to check up on me and go through that. That'll be good practice, and then of course go back and do elements A and B and D. So when we get together on the next lab, laboratory number 2, it's going to be this similar kind of data, although things will change a little bit because we're going to be changing the frequency. And then lab 3, I'll probably actually pull the old scope out and film what I'm doing, because it's really interesting as we go through and we take the circuit through its parameters. We're going to watch these 2 curves cross each other, so that will be kind of neat. And I'll take that opportunity to spend some time talking more about the scope, and if you've never touched an oscilloscope, kind of reiterate some of the points that I made at the end of last term on some of the things that you want to look for on that oscilloscope. So that's where we are. You've got a week to get this, get your question sheet written up and turned in, and we're off and running. So if you have any questions, shoot me an email. Try and answer those. Take care. Bye-bye.